Welcome to Heavy Networking. I'm your host, Drew Conry Murray. You can connect with me on LinkedIn and we can be internet friends. And joining me is Greg Farrow. You can also be his internet friend on LinkedIn too. Today we're talking to Subbu Varadarajan and Kumar Sinthavil from Palo Alto Networks. They are our sponsors for this episode. And we're going to dig into a thorny problem of lossy residential networks like home wireless that your work from home folks are using to access company resources. Their Wi-Fi sucks and their use of corporate resources sucks. And yes, maybe you've got them plumbed into that SASE fabric, but that doesn't fix their user experience woes. Or does it? Subbu and Kumar have some SASE network tech to discuss today that can indeed help with the lossy home network in ways CDNs and adding new POPs to your SASE fabric won't fix. Subbu and Kumar, welcome to Heavy Networking. You've got a bunch of smart engineers listening here who know about things like WAN optimization and TCP variants. I think we're going to be talking about different things, but let's dive into the first question. So we know there are a lot of people working hybrid, remote, all over the place. So network performance isn't necessarily going to be ideal. And they're also accessing cloud applications, applications hosted in public cloud or SaaS applications where the network engineers or the infrastructure folks don't necessarily have control over how well they perform. So is that the problem statement we're dealing with?
That would be accurate. I would say, like if you go to engineering 101, you can only optimize what you measure. And I always go to the first principle when it comes to foundational problems. And what we understood was today, like you said, WAN acceleration, CDNs, they solve a good problem, was very relevant, I would say, in the early 2000s, if you will, or even late 2000s. But then we all can accurately say, thanks to all the technology we have built now as an industry, the internet is much more stable now, right? So now if you think about where the latency is occurring, so Kumar and I were measuring it maniacally to understand where 90% of latency occurs today, and that fell under bad Wi-Fi access, which I would agree, except if you're a network geek or gamer, but 99% of us connect on Wi-Fi, right?
Yeah. Yep.
And we saw a lot of variance when people are connecting. And the other aspect is what kind of application you're consuming, how heavy those applications are. And those two were factoring into the latency. And we are trying to focus on that. So you are 100% right about characterizing the latency landscape.
What you're saying is that you've done a lot of deep research onto traffic and traffic profiles, and you believe there's a way to accelerate traffic or effectively accelerate the applications. You're not accelerating the traffic. There's a way to accelerate applications here somehow.
That's right. So I think when we think about accelerating an application, what we really mean is how do we reduce the latency? How do you reduce the response time of the application? You click on something, how do you make sure that your app gets that content instantly without having to worry about the large data set that the APIs need to crunch? Similarly, if you're going to connect from your home Wi-Fi, if you're going to connect from airport, Starbucks, how are you going to make sure that even when you have a very crowded place or you are having a bad signal to noise ratio, how are you confirming that you get those packets as fast as possible, right? So those were the elements we were focused on, which is complementary to the underlying technology that was built before. But now we started to focus on areas where there's a lot of variance and how do we normalize that experience so everyone gets the best experience.
Let me get nerdy here for a little bit. Let's try and say very early on here that it's not immediately obvious that how to do that. Like in the old days, the way we did it is we did local caching. We did some sort of proxy server. We did, we cracked open the content. We did, compression, and we did some TCP acceleration, all that sort of stuff, right? Where you could avoid stuff. That's not what we're doing here. We're doing something different. You're using sort of like the Prisma backbone to accelerate. How does that look? What am I thinking about if I'm an engineer?
Perfect. I would say, so the way I want to the way to kind of picturize this would be imagine what I call a latency landscape. And what I mean by that is from our laptop, we connect to our Wi-Fi. From Wi-Fi, we connect to, say, Prisma Access. From Prisma Access, where a lot of security processing happens for your protection, then the packets get routed, forwarded to the mothership where applications are running. It could be private apps, it could be public apps, right?
Right.
And what it means is that if I name them, the place where from your laptop you connect to Prisma Access, I'm going to call that client mile, MILE. That's where you kind of connect, that's where you have all the Wi-Fi problems. And then the place in the middle from Prisma Access all the way to the mothership, we are using the backbone for the hyperscalers, where we have a private connection, and that's going to have the highest SLA in the industry, and you're going to forward the packets as fast as possible, right?
Right.
And those are managed network. That's what I call maybe 1% of the latency lies, right? And that's well managed.
So it's sort of that last mile.
The last mile comes from the hyperscaler
yeah.
into the application, right? So
Right.
we call that the last mile, or the cloud mile, if you will, or the app mile, where the
Okay.
app
Yeah.
servers are running, and it's going to take some time crunching those requests for us, right?
Right.
So here, if you think about, say, if you're going to go to a very, I'm going to say, rich CRM solution that all of us use
Mm-hmm.
heavily, right? And if you think about it, say a dashboard takes 20 seconds to render. It's not that they don't have the fastest computer in the world. They do. It's not like their APIs are not efficient. They are hyper efficient, right?
Mm-hmm.
But it still takes 20 seconds. So
Yeah.
how are we going to reduce the 20 seconds? And when Kumar and I looked at it, we understood two things that kind of stood out for us. One, same user, same page, they were getting different experiences. We were trying to wonder why is that, right? Because if you're going to download the same thing under similar conditions, you should expect the same response time.
Yeah.
But it was changing. So at the outset, what we immediately saw was, depending on the load on the cloud, the response time for the same API changes, even though we are working on the same data set. We thought that was one thing, but that's something that SASE providers cannot control, right? That happens on the application side, and we don't know how much traffic the application is going to get, right? It's going to get traffic from all over the world, including the SASE providers. And the second thing that we thought was contributing to the problem was your connectivity. Even though I'm kind of connecting to the same place, I found that I had intermittent packet loss. Sometimes it would take, I'm going to say 250 milliseconds, and sometimes it
Mm-hmm.
may spike to 500 milliseconds for no reason that was obvious right away, right?
Mm-hmm.
Then what Kumar and I did was we started to take packet traces.
Right.
And what we found was super interesting. We found that even though my laptop is in the same place, my Wi-Fi access point is in the same place, there is intermittent packet loss. It's not persistent. It happens, it comes and goes. But
Right.
that had a
But it
dramatic
shouldn't
effect.
be, right? The Wi-Fi should be more or less the same. The uplink speeds should be more or less the same. The backbones, we've generally got plenty of capacity in the internet backbones, but you're saying packet loss occurs regardless. It just happens for reasons not immediately obvious, or did you find them?
So it was not immediately obvious. The reason is these are not persistent problems, right? If you're going to sit at a place that's far from an access point,
Mm.
that has a poor signal to noise ratio, then you would say most of the times you're going to have a bad experience because you have a poor signal to noise ratio.
Mm.
How would you explain that I have a good connection and all of a sudden I'm having a bad connection,
Mm. Yeah.
right? And then it self heals. And that's the worst part about it is when it heals automatically, and when you take a packet
Mm.
drop, you're going to have a picture perfect packet trace.
Yeah. Brownouts are worse than blackouts. If it's broken, it's broken and you've got
Yes.
something to fix. If everything's green, it's fine. But when it's a brownout, it's like, what went wrong?
So you remember the time when we were measuring the packet loss just outside our office at a bus stop.
Yes.
We don't have to change the place or location. Your device is still the same.
Yeah.
Your connectivity is still the same. But just like the surroundings, when a bus just went through past us, the performance varied significantly.
Yeah. Because as soon as you drop a packet or a group of packets, you have to resend them. And so it's not like one round, it's two round trip, and then everything after that goes backwards in the queue. There's a compounding effect for any sort of disruption to the flow.
Exactly. Well said, Greg. Right? It's the back pressure, and like Kumar said, like we found that to be extremely fascinating. That same device, same battery level, roughly, but then we were experiencing different levels of performance for a very simple transaction like downloading a static image.
Right. Yeah.
So then I guess the big question is, what can you do about it if, in the examples that we're talking about, IT has very little control over any of this. They don't
Exactly.
have a lot of control over the Wi-Fi connection. They don't have a lot of control over the, for instance, a SaaS app. So where can you start to have some influence?
That was the next most interesting thing for us was these are happening at, I'm going to call it portions of the internet that are outside the control of IT. Like, for example, we don't control how developers are creating new applications, what kind of data set they are crunching. That happens continuously. On the other side, we don't control how employees are going to access the internet. They may be traveling, they may be coming from home network, which is not enterprise grade. And under all these circumstances, how do you figure out that these things are occurring? And what makes it more challenging, like Kumar said, these things can occur in a random manner. And when they're occurring at a random manner, it's not like I can use the data to say, oh, Greg had a bad experience at 8:20 in the morning. So he's going to have a bad experience again at 8:20 in the morning tomorrow. It doesn't work that way, right? Because these are happening based on conditions that are surrounding you, right? You might be in a crowded place. You might be in a place where your neighbors might have a Wi-Fi that's in the same band as you, and that's triggering packet corruption. So these are things that can happen for reasons
I
that
like
we.
the one you said where battery, if a laptop's running out of battery, it might go into a power save, and the Wi-Fi might go into a situation where there's not enough voltage, or it might go into a sort of a power saving mode. Because Wi-Fi 5, 6, and 7 all have power saving modes that may be invoked or not, right? But it could also be a car goes past, it's got a faulty electrical and is doing something with the spectrum. I guess the question here is, how do you detect, like if you can see the packets being dropped, what are you going to do then to smooth it out? Like in the old days, we used to crack open the SSL and cache it locally, and then we could do various things. But what are you doing now? Because we've got to do this at scale, right? Because we're now working at gigabit LAN speeds or home speeds in the hundreds of megs. What are you doing?
Yeah. So, two important research actually occurred in the industry that was very helpful for us to start from a good place.
Yeah.
One, there was a paper that was published, I believe, by MIT that talked about buffer bloat problem, right? So the idea was, hey, can I cache all these packets intermittently in my router so that if someone loses the packet, can I send them back? And that had a it actually failed because the more they stored the buffer, it actually had a counterintuitive effect where it was causing more latency than helping. And the second problem that I think was fascinating was the battery point that you talked about. So the what we found was it's not how much content you download that affects your battery, but it's how often you turn on and turn off the transceiver that affects your.
Right.
So if you're on a bigger device like a laptop that has bigger battery that has a different characteristics from say your cell phone, which has a smaller battery, so the engineers have taken a more conservative approach on how to preserve that. All those would translate to what we call signatures or client device capabilities, right? So what we started to understand was under ideal conditions, let's first profile what happens when someone connects from, say, Windows operating system, Linux operating system, Android operating system, iOS, etc. And we found right out of the bat, it was not the same. All of us know that all devices have different characteristics because it's built for specific conditions. And we found that every operating system behaves differently.
Okay, so here's my problem with that, right? What you're effectively saying is that every person is different. Every situation is unique to that user. How do you bring a technology and generalize it for everybody's unique situation? That's the challenge I can't understand. Are you saying you effectively create some sort of mechanism to say, I'm watching what happens to this flow, and now all of a sudden I can apply it per user? Is that what you're saying?
That I would say, you're pretty close to what we do. One is we try to understand what is the ground truth, right? Given a set of constraints, like what device you're coming from, what network you're coming from, I can kind of understand what should be your experience. But what we wanted to add to the equation was what kind of an application you are consuming. Is that a real-time application? Say, for example, Zoom is a real-time application. Or is that a near real-time application? Are you watching a live content? It's a live streaming event. It could be a webinar, or it could be like a live sports, right? So we call them near real-time. And then are they like more interactive application? Like if you're interacting with some of the top enterprise apps, like Google Drive, Salesforce.com, SAP, right? These are interactive applications. So once we understand what type of application you're consuming, and what are the kind of devices you're coming from. We have an opinion based on, I would say, a couple of trillion transactions. We kind of characterize them using large data set on what your profile must be under ideal conditions. Now we compare that to your unique condition. And when we understand that, let me just geek out a little, Greg, right?
Yeah.
What we found was, so if you think about a traditional TCP/IP stack, by the way, both Kumar and I, we are crazy fans of TCP/IP. We believe that it's built by gods. In fact, the company was founded, in the halls of uh, Park.
I know we can argue, but one day when we have a beer, we'll argue. I would highlight the inefficiencies in TCP, but I take your point. The point
No,
is that it's lasted for 50 plus years
exactly.
unchanged. It's a
Exactly.
miracle that it even works at all, really.
Oh my
But the fact
God.
that, yeah,
That is the point, right? It's a very
yeah,
humbling experience. Like, think about a technology that was built so long back that it's still making the internet work, right?
mm,
What we wanted to do was, what we did was something, we just helped the underlying TCP/IP application by bringing in the context of network, device, and application. So what we did was we said, going back to my geeking out part, when you have a packet loss, when you have a packet corruption, all of that actually translates to only one signal in the traditional TCP/IP, which is packet loss. I sent something, packet did not make it to the client, so it manifests as a packet loss from the client, right?
hmm hmm
That's the only signal that I was operating under. What we did, we started to measure what we call like micro disturbances. So as packets are going through, we measure what kind of a disturbance we are getting based on the ACK. And going back to our first principle point, you can only optimize what you can measure. In this
yeah.
case, we were measuring these micro disturbances. And that was different for different people. But we also know what should be
So
your
you were
ideal.
able to find an algorithm that could detect these or notice these or signal these, and then be able to put that into the Palo Alto Prisma platform and say, I see these flows going through here, therefore I can make these changes to the flows to improve the performance.
Exactly. And
Right.
let me give you an example that happened with our with a very big customer of ours. They are actually a big streaming giant, and they use some earth-stunning events. I've not gotten the permission now to name them, but they're very, very incredible customers, and we are
Mm-hmm.
now we have become good friends over time.
Mm-hmm.
And they were using a top CDN to do all their live event. And then when we went there, we were at that point we were not part of Palo Alto. We were a small startup with very finite resources, I should say, compared
Yeah.
to what Palo Alto has.
Uh-huh.
So our technology was built with I would say 1/10 or 100th, you would say the number of pops like this big CDN.
Yeah. Yeah.
And then we went and told them that, hey, we have this technology that measures all these packet losses and stuff, and we understand the app context, and we will make it better. They were actually very cynical, rightfully so, because they were using the
I,
best.
I've got to tell you, I'm a bit cynical, right? Because what you're saying here is you're sending packets. There's a bunch of users, thousands of users out there. They're sending in packets to a known service, Microsoft Office, Office in Azure, SAP, Salesforce, or so forth. And if you send it through a middle box, you're
Mhm.
saying that you can groom that traffic flow to effectively accelerate and adjust for problems in the backbone and problems out, say, at the edge where the laptop is, where the Wi-Fi is not working.
That is, I would say, you are right to be cynical because
Sure. Yeah.
the
But
way,
I'm understanding the problem, right? That is,
yeah, that's the
yeah,
accurate depiction of the problem,
right.
Greg.
Yeah. Mm.
And I would say I actually like people who are cynical because I found most of the cynical people to be intellectually honest. And what I mean by that is if you present the
hmm
data to them, they would be able to understand why the data helped them or hurted them.
Yeah.
As compared to, because they have a reason to be cynical in the first place, right? Because they work on some set of metrics. So
Yeah.
when we went to this customer, we did an A/B test where 50% of the live event was subjected to the existing service provider, and the other 50% was given to us. And what they found was all the OTT providers, they live and die by three metrics, Greg. One is
Yeah.
called the VST, video start time.
Yeah.
rebuffering ratio, how often your stream stutters, right, when your audience is watching it. And the third one is the average bitrate. What is the
Right.
quality of the stream that they're consuming? And these are all multi-bitrate streams, right? And what they found was in each of those metrics, we were able to outperform the stop CDN. And this
Right.
person is so intellectually honest, like I have so much respect for this person. He
Yeah.
actually flew to US. It's a European giant.
Yeah.
Is
Yeah.
here, right? And he met with me and he said, "How did you outperform them?" Right? Explain to me. And what
Right.
we showed them, Greg, was we showed them what we measured first.
Yeah.
We showed them that almost 50%, right, Kumar? 50% of their the flow had packet loss.
See, the reason for the 50% is you will not have this packet loss consistently. Not all 50% of the connections is going to have degraded performance in a consistent manner. It
Yeah.
occurs
Yeah.
and then it goes away.
Yeah.
But when it occurs, the videos, your experience, the viewers' experience degrades significantly and they
Mm.
can drop off. Right.
Yeah.
So that is why, so the measurement, what we did is to monitor every connection that goes through our system
Right.
continuously. And
And to
that's,
do it per user, right?
yes.
And what you're looking to do here is what I talk a lot about is good put. Just because you've got a 10 gigabit circuit doesn't mean you're getting 10 gigabits of useful data. Most likely you're getting 8 or 7 because you overload a buffer somewhere or you're dropping packets in the laptop NIC or the server's had a spike while it processes someone else's request. And so, or there's packets being dropped and then you have to retransmit, but the retransmits isn't useful bandwidth. It's dead bandwidth because all those packets that you drop, which might be megabytes of data at high speeds, right? At 10 gigabit pipeline,
Mhm.
you've got megabytes in flight. And so if you drop it, you've then got to resend megabytes and then queue up everything about it. So you end up with the situation of how much good put there is on your circuit, not throughput.
Oh
Throughput's a
my
measure of
God.
what you good in
That,
perfect condition. Good put's what you actually get. But it sounds to me what you're saying is you track every user, you watch their flows, you fingerprint the host, you fingerprint the destinations like the services, and then you can then fingerprint the user's profile, and then you can modify the traffic flow using algorithmic methods in a middle box to effectively groom the traffic into just sending good put and not trying to accelerate through throughput.
so I would say, for first of all, you should have joined our startup back then
Yeah,
because the way you were kind of depicting is very close to how we shape the packets. We call it packet shaper. So we
yeah,
would shape the packet for every flow. But what was interesting, Greg, was your good put terminology is what was our guiding, it was our North Star. We would know that under a given set of conditions, this is where a user flow must be to have optimal throughput. And if you're falling below that, we're now
yeah.
trying to understand what are the signals that were preventing you from reaching your max throughput, your good put.
Let me just ask a second probing question. So one of the things we have as problematic in the whole pipeline here is buffer bloat. We send too much traffic, and
Mhm.
there are buffers in the pipeline somewhere along that are either holding onto the packets for too long, or you get these spikes which overload, and then you get packet drops. It
Mhm.
sounds to me like your algorithms, which are just pacing out the packets, um, I say just, I mean, pacing out the packets is actually quite a thing to achieve, is you're actually detecting that there are problems on the network. And whether it's buffer bloat or buffer overload or latency on a given circuit, you can actually groom around that because it's all algorithmic.
It's algorithmic, and what's powering that is the application context. If
Mm.
you remember when I said, hey, there are factors that are network based. Are you coming from a mobile network? Are you coming from Wi-Fi, home network, etc.? Right?
Yeah,
There are factors that are device capabilities, right? Are you coming from laptop, um, IoT device? Is it your cell phone? And what operating system you are functioning on? These are what we
yeah,
call fundamental parameters. The fourth one that we added that was unique was what we call app context. This
mm,
is why we were talking about real time and near real time and all those applications, right? Once we understood the app context, this buffer bloat problem that was occurring before can now be managed because previously devices, intermittent devices, were agnostic to application, whereas we are app aware, right? So when we
yeah.
make decisions on how to shape packets, how to send the packets out, it's in the context of the application. And it's not agnostic where we are just holding on to the buffer without the context of the app.
So can I ask your position as essentially an intermediary here, and you're able to measure essentially both ends of the connection. And if the issue we're dealing with is dropped packets, does this mean you're essentially caching individual packets? And if you detect a drop, you're resending on behalf of that flow as opposed to having to wait to each of the endpoints to figure out, oh, this packet dropped? What is the mechanism here?
So I would say with the app context, Drew, right? So if you're talking about an application, say for like Zoom, for example, if you cache the packet, and especially for audio packets, if I retransmit the packet, every audio packet is playable, and you will hear the click sound if I retransmit the packet, even though it could be a few milliseconds away, it might actually disrupt your experience,
Sure.
right? So we can't be doing that in an app agnostic way, but for in the app aware context where if we understand that these packets can be resent, then we would actually preserve them and then we would send them in the context of the stream. Not we don't cache them persistently.
Well, caching inserts latency. Right?
Yeah.
If you cache something, and you either have to break into the SSL, for example. There's a latency in the processing latency, the cache latency, retrieving from cache. When do you transmit? There's serialization. So you don't want to cache until you have to.
Correct.
And at low speeds, where we were a decade ago so if anybody's thinking of WAN acceleration, so a decade or 20 years ago before SD-WAN, we were doing WAN acceleration, and at low speeds, like 1 meg, 10 meg, 50 meg, you could do this in real time and it wouldn't impact the flow. But when you get to a gigabit or 10 gigabit WAN circuits, the actual latency that's injected by traditional WAN acceleration is so large that you're actually making things slower, not faster.
Exactly. I think the way I would like to characterize that is as technologists, we create a solution for a specific problem, right? But the problem is continuously changing. I call them the shift in the problem space. Like you said, it was very relevant in the early stages of the internet, and now the problem has shifted. Now the applications are more dynamic. They are changing by user, right? So when we talk about are you shaping packets by user, if you think about it, the applications are also changing the response by user, by time, by context. And what it means is that as computation power is increasing and the user expectations are increasing, the apps are becoming more dynamic. And what was missing when we came into the world was we found that the infrastructure is not adapting to how users are consuming these applications. It was more like it was like a fixed, rigid pipe that was simply copying packets from left to right. And we thought, hey, if you bring the app context, now the delivery infrastructure now can adapt based on how users are consuming the application. And that enables us to do very, very interesting things, right? To kind of give a geographically consistent performance.
And now the key here is that you can use Palo Alto's Prisma Cloud to do this middle box functions. It's not like I have to buy a hardware box and do this. Or do you? Do you put it in the appliances that go at the edge of the network, in the branch, all of the various SASE appliances that we put, or do you do it in the cloud, in the center?
That's a great point. So first of all, once we came to Palo Alto, we could understand the power of Palo Alto, right? How much resources we have and what kind of infrastructure power we have. And once we took our secret sauce and we applied it, it's basically cloud delivered, right? So you don't need a hardware, you don't need to put anything on the client side, you don't need to change the client code, if you will, from the app. You just need to enable it in Prisma Access. So it all occurs inside our cloud infrastructure. It's transparent and the users get the best experience.
So I guess what I still don't understand then is what is it exactly that you're doing to boost this performance or shape these packets to mitigate issues like packet loss or brownouts?
Let's take a simple example, right? So imagine without our technology, Drew, you are coming from a Windows box and Greg is coming from an iOS box. And both of you are consuming, let's take a very simple content. You're downloading a large file. What happens is, in a typical context, for you, Drew, the way it works is you would make a TCP connect, right? And then once you have a TCP connect, your client device would start advertising more and more packets. You'd say, now I can get 10 packets, 20 packets, 40 packets. You keep increasing till you hit what I call, and we use the Greg's point, good put. That's the maximum thing that you can consume safely without getting drowned by packets. Yeah. But let's take the same example for Greg. While he was ramping up, he had a packet loss problem because he was in a congested place. but he's coming from a device that can handle a lot more throughput, but he had an intermittent packet loss that he did not anticipate. So what his TCP/IP stack would do is it would inadvertently think that's the peak limit for him. Then he will start to ramp up slowly, right, from that point. What we understand is we would know that for Drew, the good put must be at X megabits per second, whereas for Greg, it should be at Y megabits per second, right? What could be those numbers? But then we would know that Greg did not even reach his good put, but you did. Because we see that Greg had a suboptimal experience and is still trying to ramp up, we contextualize that for the TCP/IP stack so that we would understand that, hey, he should have been at level Y, but he is at like half that level. So we are now trying to see if we can ramp him up quickly without losing time so that he can go back to that level. While understanding, can he consume it safely?
You've got to remember too that the buffers could be using different algorithms, right? So the client could be using Red or BBR or Reno or Vegas or Cubic. And so its rate at which it sends out packets is radically different. So iOS uses one algorithm, Windows uses another. But every router in the path is also going to be using a different buffer. This is the failure of TCP. It's not TCP itself. It's the fact that every implementation of buffer is not the same. So you can't predict what's going to happen.
See, this is where it gets really interesting. The thing that you brought out was, say, TCP, we have been fan of TCP since day one. It has grown so much in the last 20, 30, 40 years, right? Where they started it for rigid network, and then all these algorithms evolved to maximize the throughput for the customers. But even in such cases, say whether they go with Reno or Beck or Quebec, they're trying to optimize the congestion and maximize the good put, like you said.
Yeah.
But this is a standard algorithm for all connections, for all applications in place. What we are measuring here is for every connection, when we measure what's coming through the connection, different signals that we get, we understand where the degradation might happen.
Well, you don't have to understand the degradation. You just have to measure it, right? So
yes.
It's like putting a heart monitor on a patient. You can't see the heart, but you can get all the information that you need from the heart monitor. You can see the pump, you can see the electrical signals, all that sort of stuff. And then you can make decisions. That's what you're doing here in the middle box.
Detection part, right? So once we detect this, like you said, we are measuring this, we are detecting something has to be done.
Yeah.
So the next thing, what we do is we are not touching the TCP/IP stack. That's doing its purpose, whether it's Cubic or whether it's Reno, it's doing its purpose. In parallel to that, we have built our own packet shaper. So this is where our proprietary algorithm comes into play. So the signals that we have measured now feeds into this algorithm to say, what is the mitigation action that we need to take using this packet shaper, in addition to what the current TCP/IP stack does.
But the secret here is that you're doing the shaping per user, per endpoint, not per application, not per flow. And then what you're also doing is using various signals into the packet shape. So you're not just looking at the packet shaper and saying, I need to rate shape this single flow, this user's flow to a single app, which is still very granular, to 64K or, 1 meg or something like that, right? You're actually saying is, I can see I'm getting signals here in the flow to say that look like Wi-Fi problems at the local end. And therefore I can predict certain things about this. And because you're gathering so much data so this is also a machine learning exercise, right?
It is actually very much so, Greg. I'll try to kind of simplify it a little bit more. So if I am app agnostic, what I mean by that is my TCP stack is basically a packet. It just takes packet from the left and it's going to optimize it for the right?
Yeah, the application sends datagrams. The datagram turns into a packet on the wire. Yeah.
Right. And so it has no idea how many packets are going to come from the application in the future. It only operates based on what it has in its current buffer, right? If the buffer if the buffer has packets, it's going to send it based on the maximum the client can consume. What we did when we said we contextualized it, to your point, we are kind of measuring all these micro disturbances that's happening on the wire, but we are also getting the app context. So we basically wired our application to our kernel to give app context in real time to our TCP/IP stack. And when Kumar talked about the packet shaper, what we really do is as we get that packet from the application, we are actually letting the TCP IP know, are there going to be more packets or not? Because if I'm just operating in the TCP level, I don't know if a particular response is done or I'm going to get more responses, right? But in our world, we would know that more requests are coming and more responses are coming, and we are constantly giving that additional context to a packet shaper.
And how do you get that context for that application?
We get that based on the request flow that's happening on the invert side, so from the client side, and
Mm-hmm.
we understand that these request flows are so. So if I take an app agnostic view, I would not know that there is a request and response that's occurring that leads to these packet flows.
Mm-hmm.
I'd be simply working on a signal that I have packet in my buffer, so I need to send it, which means that I cannot plan for how many I need to send, how I can club them together. I don't have any of those signals to make a better decision, right? I'm more reactive. The
Mm-hmm.
more you contextualize, you understand that, hey, this is the request, this is the response, I'm going to get these many bytes back. Now I can do many interesting things, right? So going back to WAN acceleration, which we call east-west acceleration, which is data center to data center, we are operating at gigabits per second speed. Whereas north-south acceleration, which is happening from cloud to your device, that is not going to operate at the same speed as cloud to cloud,
Sure.
right?
Yep.
So
Yeah.
we would now understand that for a given payload, I need to have, say, 100 megabytes of content that's going to come. I only got 50 megabytes of content. A traditional TCP won't have that context. But
Yeah.
our TCP would have that context because we have built that context in from the application to the kernel.
And just to restate this, it's all done in the cloud. So in the Palo Alto Network's Prisma cloud. And this is, I mean, as best as I can understand it, this is just something that gets added to your existing Palo Alto product stack. So if you're using Palo Alto Prisma and you're using their SASE service, this is just something I can go and turn on. Is that the idea?
That is very true. So it's a turnkey solution. So if you
Mm.
just buy App Acceleration, which is an add-on to your Prisma Access, you would now have this ability to accelerate applications to all of your workforce, your distributed workforce, not just the folks who are uh, what I call fortunate to live by the cloud's backyard, but for
Yeah.
people who are all around the globe, like Australia, India, right?
I imagine this product works really well on long, fat networks, LFNs, which is, you know, latency and measured in the 100 milliseconds to 200 milliseconds, and does a lot of data in flight. This would be have a lot more effectiveness on those flows than it maybe would on short haul flows.
Yeah, in fact, the thing that we found that was super interesting was we did a thought experiment
Yeah,
where we said, hey, can we just increase the pops and would that automatically increase the response time,
yeah,
right? So as a startup, we were doing some experiments to kind of understand where we should invest our dollars.
mm.
And what we found was you increasing the number of pop does not automatically increase your throughput.
So what you're saying there is having a bigger backbone, so more pops in the middle boxes. So having more middle boxes in the internet didn't accelerate your throughput particularly, or it didn't accelerate the good put.
Yeah, it did not increase the good put in a linear manner, right?
Right.
So I'm not saying you should just have one pop in the world. You should have, but you don't need thousands or you don't need like hundreds of pops. And then what we measured was we took one more step. That's where we started to understand the latency itself, and we found that application latency would eclipse your pop efficiency that you bring to the table. Because if
Yeah.
something takes 2 seconds to respond, it doesn't matter whether you have 2,000 pops. In fact,
Right.
I tell our customers, imagine taking a very big enterprise application that you use and you
Mhm.
put that application inside your laptop. Now you've eliminated all the network latency. But if you click on something that's still going to take time, and the reason it takes time is because it's doing all the database lookups, it's doing all the other orchestration to
Yeah.
render what you want, right? And the only way you can subsume that latency is if you're app aware. And that's where, we introduced our bot technology where we would spawn a bot that has the application context. It would know how to shape the packets on the wire because
Yeah.
it knows how many packets are coming, what is the context. It also understands what APIs have a long pole when it comes to response time. And it's trying to make that a more proactive model than a reactive model.
Okay, so you just said something interesting there. You said you spawn a bot. What does that mean? What are you spawning that bot for, and what is that bot doing?
Yeah. So the way we want to kind of build our technology is if you think about the traditional way of attacking latency problem is by caching the content or
Hmm.
by doing WAN acceleration.
Mm,
Those things would work great when the content is not changing, right? Especially the caching part. If
mm,
I computed a content, let's say it's an image, and I computed it yesterday. When I say I computed, I created that image yesterday using computers, right?
Yep.
That image is still relevant for all of us when we go to an application. That means I can cache them and I don't have to depend on the cloud and I can deliver them.
yeah.
Yep.
So I can give you an example there. I worked for a large bank and I put in a caching proxy,
Hmm.
and it used to save extraordinary amounts of traffic. Something like 40 to 60% of the internet capacity was saved.
Hmm.
And the reason is that at lunchtime every day, 20 to 30,000 people would all go and look at the same news sites. They'd go to a newspaper site to get the latest news. And we only had to fetch that once for 30,000 people instead of having to fetch it 30,000 times. Now,
Exactly.
that worked 15 years ago, 20 years ago, whenever that was, but it doesn't work now because everybody's using progressive web applications or single page applications. And every rendering of the page is unique to the user because you think about Salesforce, you log in, it doesn't show you everything that Salesforce offers you. So not all the objects are the same. And they all have different IDs. They get globally unique IDs for each element, for, all this stuff. So the old ways of caching don't work with modern web apps because of that.
Like when the world was simpler, where, in your banking example, you talked about you can cache it and the
Mm,
same content goes to 30,000 users. That was a great problem that was solved by a great solution, which was static content caching, and you were able to reduce the load. It was a
mm,
quantifiable way to say that that solution worked for that problem. What happened today is same APIs are getting different responses,
yeah.
which means now if you apply caching, you're going to break it. And or even worse, you're going to risk leaking what I call a sensitive information to others who don't have access to it.
Mm,
So in this modern world where the response is changing dynamically, so the traditional caching will not cache them. So which means that you have to now route the packets all the way to the mothership, wait for the response to get ready, and then that gets delivered all the way to the client, which leads to latency. What we thought we
mm,
can combat the problem is if you understand what I call the user intent.
mm.
And I always ask this question, right? As users, the way you would interact with Salesforce.com would be very, very different from the way you would
You're
interact
gonna
with.
you're gonna throw some intent-based networking at me in a way that I haven't thought about it before. Because what you're actually saying is you can predict what the user is going to do when they try to connect, as you say, to Salesforce. Then the user's intent is to render this page as quickly as possible, and you can determine that because you can fingerprint it in some way.
Exactly. So we are trying to understand how a user journey, we call
Mm.
them user journey, which is a series of clicks a user would perform inside the application. And
Yeah,
as we have this, I'm going to call it like the user journey across millions and millions of users, it gives me what I call a heat map. We call that an app graph. This app graph enables us to understand how the user journey typically unfolds within the context of the application. Second, it also helps us understand what APIs are the long pole when it comes to response time. Like what takes most time, what is very snappy, what is not snappy.
hmm,
Once we understand these two, now we go back to how we shape packets, right? So we would tell our TCP IP stack that hey, these are going to take more time, these are going to take less time. But then we also use our bot to go ahead and get content that we believe will take more time, especially if we understand a user journey is going to take that route.
yeah,
But we only do that if we believe that you're going to take that route, else we will not go and
yeah.
get that
But
content.
that's the unique thing here is you're doing something that I worked in a lot of traffic control and proxies and caches and traffic shaping and all that sort of stuff for decades. And the ultimate goal was to effectively do traffic shaping which means packet shaping or flow shaping down to the per user level. And that's something that you can only do now because the technology enables it. That is, in the Prisma cloud, you've got the ability to see all the flows. You can fingerprint those and know which ones are coming from a user, and you can take various signals and effectively look for when the buffers are failing and flow shape for the user to make sure that they're getting the actual best possible experience and you're actually doing it not only per user, but per user and per application.
Exactly.
And that is that's a really transformative. I'd be interested to hear how many people in our audience will try this. And if they do go out and contact Palo Alto and start saying, I want to do the app acceleration and do a trial, I'd be interested to hear from them when they do it.
Yeah, I mean, we actually go and lead by saying that you come and we would show you how to measure your current state, right? So that we can give you a full view about what's occurring in what's occurring for your employees, your contractors, partners. We give you a full landscape of who's having a good connection, who's having a bad connection. We don't stop at that. We also go and say how many of that we remedied so that they had a better experience, so that your trouble tickets, your support tickets is going down, right? So we're trying to give you a full measured way of saying that, hey, this is why this is going to be helpful to you, right?
Yeah.
Second thing, we also say these are the applications that are heavily used by your workforce. And when they use these workforce, this is how much time they would typically be waiting.
You know these because Palo Alto sees these, right?
Yes.
You know which are the ones people use because Palo Alto is an established company. It's huge. You've already got so many people using Prisma SASE. And so you can make smart decisions about which applications to do the acceleration on first. But over time, it's going to grow. There's one thing that strikes me here, and you may not have the answer to this. It feels to me like we talked a lot about the endpoint and Wi-Fi, and we've had a number of companies talk about optimizing the user experience by putting an agent in the endpoint, maybe inside an app or something. That sounds like something that you should be doing at some point.
I would say you should never say no to any good idea, Greg.
Yeah.
So the way we started, like what you can do as a startup is different from what you can do as
that's right. Yeah.
Right?
Supporting hundreds of different versions of smartphones versus apps on a smartphone versus apps on a Windows or a Mac or whatever. So, but it's the one place where you can actually also really accelerate. If you can get into the client operating system, you can do things with applications. So it just seems maybe you can talk about it at some point in the future.
We're looking forward to it.
Okay, well, I feel like we could keep talking much longer, but we do need to wrap up. Subbu, if people are playing with this on Prisma SASE, what kind of metrics should they be looking for to say, okay, yes, I actually am seeing a difference in performance?
Yeah, that's a very good question. The way we want our customers to understand this or to measure this is to look at two core parameters that affect the application experience. One is how fast we can send the packets to your device. We call them throughput. And we actually help them say, hey, this is the max throughput that we were able to deliver for a given application, or we can also help them see it on a per user basis. And the second thing is what is the latency that they were experiencing when they were clicking on certain features in the application. We measure this by looking at the response time for the application. So we would tell our customers that typically the application took X seconds to respond, and we got that down to Y milliseconds so that they can see the difference in how fast we accelerated the response time for the apps. And we also give them the throughput so that they can now see how fast their apps were responding and how their users were actually getting all these responses, regardless of where they are distributed in the globe.
Excellent. Well, you do have two cynical hosts here and also a cynical audience. So the opportunity for them to actually look at it and see the numbers for themselves would be welcome. If you're interested in finding out more about app acceleration from Palo Alto Networks and their Prisma SASE, you can go to paloaltonetworks.com/SASE/access. That's paloaltonetworks.com/SASE/access. Thank you, Subbu and Kumar, for joining us and for Palo Alto Networks for being a sponsor. We really appreciate having a deep dive about TCP and everything else. If you as a listener, thank you as always. If you're listening, if you're ringing up Palo Alto Networks to talk about app acceleration, please let them know you heard about it on the Packet Pushers. Take a moment to connect with me, Drew Conry Murray, and with Greg Farrow on LinkedIn or via the Packet Pushers community on the Slack channel. You can also leave a comment about the show on the episode's landing page. You can find the links to all of that and take a quick look at the new and redesigned packetpushers.net. It's oh so shiny. Last but not least, remember that too much networking would never be enough.